today's class. From today, we will get started with longitudinal dynamics. So we have looked at three modules from a big picture perspective, right? As far as this course is concerned. So if you recall, we divided this entire course into 5 modules. The first module was on getting an introduction to dynamic systems theory, the transfer function and the state space representation, notions of stability and performance, and the corresponding criteria and quantification. I am sure by now it would have been clear to all of us why we did that, right? So you would have already got a flavor of it when we did lateral dynamics, right? We applied all those concepts. So we are going to continue applying those concepts, okay? And second module was a very brief recap of Newtonian mechanics. Once again, I did it. By now, I'm sure all of us would have realized because we had to use Newtonian mechanics to derive the equations of motion. We are going to continue doing that. And then we looked at lateral dynamics, where we considered both the kinematic and the dynamic bicycle models. And we did evaluation based on that. May I request everyone to mute the microphones if they are not done so. Thank you. So we looked at lateral dynamics of the linear bicycle model, and now we are on to longitudinal dynamics. And as the name indicates, we are essentially interested in figuring out, like what happens along the longitudinal axis of the vehicle, right? The dynamic phenomena which happens along the longitudinal axis of the vehicle. And primarily, we have two phenomena that we are interested in. One is what is called drive or traction. So essentially, we will be looking at what is happening when we accelerate the vehicle. We essentially are cruising at a constant speed and so on. Right? So people will talk about drive or traction dynamics and so on. So the main component here, which we need to include from the automotive system perspective, will be also powertrain dynamics. Of course, we need to look at the overall vehicle, but then the response of the powertrain also becomes quite important. The second aspect in longitudinal dynamics is on braking. Of course, here the brake system dynamics comes into play. So the brake dynamics becomes important. So as all of us know, we use the brake system to decelerate the vehicle whenever necessary and stop it when we want, right? So we are going to look at what are all the different forces that act on the vehicle during these two phenomena. And we are going to relate the corresponding forces and the acceleration, speeds, and so on. Okay? So what are the forces that act along the longitudinal direction when we want to analyze longitudinal dynamics? So we will be having aerodynamic drag. So people also call these as loads, right? Because these are loads that the powertrain need to overcome. So we'll have what is called as rolling resistance. So you look at all these forces. I'm just listing them a priori. So then we will look at what is called as grade resistance. So grade resistance is a decelerating force when we go up a grade, and it has the opposite effect when we come down the grade. Then we have what is called as drawbar pull, which we encounter when we are towing some component along with the vehicle, the primary vehicle. And we also have either the drive or the brake or the braking forces, okay, depending on whether we are accelerating or decelerating. So these forces occur in the tire road interface. Okay, so that's where they are encountered. Okay. So these are the main forces that one would look at, and essentially, a model of longitudinal dynamics will try to correlate all these aspects together. Okay, and then will relate them to the accelerations and the speeds. Okay, so that's what we will be pursuing. Okay, as part of this particular module. Now, if you look at these forces, if you look at aerodynamic drag, rolling resistance, and grade resistance, when you go up on a grade, drop or pull, all those are resistive forces. Okay, so in the context of even acceleration or powertrain dynamics, they are also called as loads. Okay? So loads, okay, that are these forces, these are indicative of the forces that the powertrain needs to overcome during acceleration or drive motion. Okay, so powertrain needs to overcome during drive. Okay, the drive from. So on the other hand, these same forces will aid braking, right? So as we know, aerodynamic drag, rolling distance, a grade resistance, or going on a slope, drop or pull will aid braking. So we need to carefully analyze, right? So the impact of these forces on both these phenomena. Okay. So consequently, what we need to do is the following. Okay. So we need to ensure that we carefully analyze both sets of phenomena, and then like we look at the corresponding dynamics. Okay. Both from the system level and also the vehicle level. So that's something which we are going to. So first, let's look at braking. Okay. So although I have listed acceleration and cruising first and then braking second, I'm going to start with braking. And the reason will become clear as we go along in longitudinal dynamics. Okay, so we will see that for most road vehicles, like braking would sort of like provide a limiting case as far as the dynamic phenomena are concerned. Of course, with the increasing advent of penetration of high performance vehicles and also electric vehicles, even we need to consider the dynamic limits during acceleration, but we shall pursue braking, and then like we will look at what happens to what is called as the vehicle dynamic limit performance, and then like we will also look at acceleration dynamics or drive dynamics, and then like we will go from there. Okay, so just to illustrate what we are dealing with, like see, if we talk about, let's say, a conventional vehicle, right, IC engine powered. So if somebody were to ask the question, like which is more powerful, the engine which drives the vehicle or the brake which accelerates the vehicle? So let's do a very simple back of the envelope calculation to get a perspective. Okay. So let us consider let's say a truck, a single unit truck, which essentially weighs around 12 tons. Okay. So let's say, we consider a vehicle of mass 12,000 kilograms, just as a representative example. As I said, this is just a back of the envelope calculation just to get an idea. Okay. So we want to go from 0 to, let's say, 72 kilometers per hour. So I'm just taking 72 kilometers per hour. The reason will be known shortly. So when we want to do the calculation, we need to convert to meters per second, right, in SI units. So let us say, like we are driving a truck, right, a single unit truck. We want to essentially go from 0 to 72 kilometers per hour in 20 seconds. So if I want to convert from kilometers per hour to meters per second, we are typically told that multiply by 5 by 18. Why is that? Because if we want to convert from kilometers to meter, like I will multiply by 1000. And then like in order to convert from hour to second, 1 hour, as we know, is going to be equal to 3600 seconds. So we do this operations. And now all of us will understand why I took 72 kilometers per hour, because it counts as a round number in terms of meters per second. So this is like around 20 meters per second. Okay. So if we want to go from 0 to 72 in 72 kilometers per hour in 20 seconds, so we can immediately figure out that the average acceleration that one needs to go from, right? So which I can write as the final speed minus the initial speed divided by the time interval in which we want to go from between these two speeds. So we can write as 50 meters per second minus 0 meters per second divided by 20 seconds. So we can immediately see that this is of the order of 1 meters per second square. Okay, so this is the average acceleration, right? So that we are dealing. So the corresponding average acceleration power. So What do I mean by this acceleration power? I'm putting it in quotes because it's a non-standard term. So what I mean by that is that, like, what is the rate of change of energy during this motion, right? So we are essentially at a bulk level, right? Neglecting all other phenomena. So we want to essentially figure out what is the rate at which my kinetic energy needs to be changed, right? And as we know, the rate of change of kinetic energy is going to be 1 by 2 times mass times final speed squared minus initial speed squared, right? The mass is constant. So that's the change in kinetic energy divided by delta. So we just substitute all the values. So 1 by 2 times mass is 12,000 kilograms. And then in meters per second, we have 20 squared minus 0 squared. So this is in meters per second. So the corresponding unit will be meters squared second squared divided by delta t is 20 seconds. Okay. So if we do the mathematics calculations, we will get it around 120. Okay. So this is the sort of like rate at which I need to give energy, okay, to propel the vehicle from 0 to 72 kilometers per hour in, let's say, 20 seconds. Okay, so as I told, I'm doing very back of the envelope calculations, right, just to convey the concept. Okay, so we'll see what the concept is. Now, we want to come from 72 kilometers per hour to 0 kilometers per hour. Okay, so what happens? So when we are braking, when I design the brake, I can't afford to come from 72 kilometers per hour to 0 kilometers per hour in 20 seconds. Let us say I am given an instruction or a design criteria saying that, hey, go from 72 kilometers per hour to 0 kilometers per hour in, let's say, 4 seconds, sometimes maybe even lower than this, right? So what happens here? So then in this case, the average deceleration that we need to worry to think about it is going to be equal to, now once again, Vf minus Vi by delta T. Okay, and this is going to be 0 minus 20 because like the final speed is 0, right? Initial speed is 20, and then 0 minus 20 divided by 4 seconds. So consequently, we want an average deceleration of minus 5 meters per second square. Of course, to be very precise, I should call it as, sorry about this, average acceleration. Okay, so deceleration by default will have a positive value. Okay, sorry about that. So yeah, so in braking, the acceleration is longitudinal acceleration is going to be negative. So when I say about deceleration, I'm only talking about the magnitude of this acceleration, right, during braking. So that's what we want to focus upon. So the average acceleration is going to be 5 meters per second square. So the so-called braking power or the magnitude of braking power will be essentially pretty much the same thing. But then once again, I'm only going to take the magnitude. So magnitude of the change in the kinetic energy, which is going to be half, Vf squared minus Vi squared. Okay, this magnitude divided by delta. Okay, so this is what I have. And consequently, if I substitute the values, what will happen? Let's see what happens. Okay, so this is going to get me half times 12,000 kilograms, right? Multiplied by 0 is the final speed. Initial speed is 20. This will give meters squared per second squared. Please note that I need to take the absolute value. Sorry, the absolute value of this entire quantity is my delta Ke magnitude, right? So divided by now 4 seconds. Okay, so I can wait for 20 seconds for this, right? So then what happens? So if you do the math, we will get this as around 600 kilowatt. So I'm just doing this example as a back of the envelope calculation to get a perspective. So we can see that although typically by and large we have a tactile sense of the engine operating, okay, and driving the vehicle, and many times we don't even see the brake or feel the brake, right? We don't get a physical sense, either visual or oral sense of the brake system. we can see that the brakes have to be more powerful, by design. Okay, so these are representative numbers, right? So typically we want to design for mean decelerations of around 5 meters per second squared, 5.5 meters per second squared. There are standards on that, so we will go to that. Peak decelerations may be even higher, right? So we will look at them as we go along. Okay, so what is the stable peak decelerations that we can get? What can be supported by a particular vehicle at the tire road interface? We will be looking at those analysis and corresponding calculations when we do further analysis of the brake system. But then I just wanted to just do this example to demonstrate that the rate at which energy is dissipated during braking, like it's quite significant, right? So under the peak criteria, it's a different matter that, like by and large, 97, 98% of the time, we may not need the full capacity, and hopefully that we pray that we never need the full capacity of the brake, right? But then by design, we need to design it for the worst case scenario, right? I hope all of us understand, right? So because the brake system is maybe the only single most important safety system available under the driver's control, in addition to a certain extent, the steering system, right? To prevent any untoward accidents or incidents while driving a vehicle. So this needs to be designed and analyzed very carefully. Okay. So now I'm going to basically consider two aspects. I will first consider the friction brake system, which is the primary service brake system available in road vehicles today, where, as the name indicates, the braking is done by what is called as a friction brake. And this involves converting the kinetic energy of the vehicle into thermal energy and dissipating it into the atmosphere. Okay, so that is what happens with the friction brake. Okay, so we will look at the disc brake and drum brake, which are typical realizations of these friction brake. We will just do a once again, very first cut analysis. All right. See, the idea of this course is also to do something with pen and paper so that like we get an intuitive insight on things, right? One can do more detailed analysis using numerical simulations if one were to deep dive into the corresponding design concept. Okay. So we want to essentially get a perspective, right, through some simple ideas from dynamics. So that's what we are going to do. So we will do that, like using simple models. We will analyze some interesting characteristics of friction brakes, namely the disc brake and the drum brake. And then we will also look at that. We will use that analysis to sort of reason out why brakes are used the way they are, right, in most vehicles today. Okay, so we will answer those questions as we go along. Okay, then after we complete the analysis of this drum brake and disc brake, we will go to the braking dynamics at the vehicle level and do a limit braking analysis and also like do analysis of vehicle dynamic limits, stopping distance, and also like we look at the concept of ABS and other active safety systems. So done like from that analysis. Okay, so that's going to be our flow of it. Okay, so if you look at the service brake or the friction brake which is used, so it contains certain important components. Okay, the first is we need a source of energy. So if we take a look at most of our, let's say, two-wheelers or even a car, right, four-wheeler with mechanical, hydraulic brakes and so on, the source of energy is the human effort, right? We have a human being applying the braking force. Of course, that's augmented through mechanical, hydraulic means. But then, like, the source of energy comes from the human being. On the other hand, if you look at a heavy vehicle like a truck or a bus, the source of energy is typically compressed air. We have seen these tanks in a truck, which is visible on which air would have been painted, right? So those are essentially reservoirs carrying compressed air, and they essentially use compressed air as a source of energy to apply the brake. Okay, so we have different types of sources of energy, and then we also have a mechanism to apply the brake. So once again, even going from a bicycle, right? So we have the hand levers, cables, and all to apply the brake. Going to a car, we have a foot pedal to apply the brake. In a motorcycle, we have foot pedal, hand lever, and so on, right? So these are different mechanisms to apply the brake. And there are, of course, the energy source is typically augmented or amplified, by various contraptions, devices, mechanisms to generate the necessary brake force and have a medium through which this energy is transmitted to from the source to the destination, which are the brakes and the wheels, right? So we come to the energy transmitting medium. For example, we can have mechanical links, right? In a purely mechanical brake. We can have the brake fluid, like in a hydraulic brake system used in a car and the LCV. We also have the compressed air, which is used as an energy transmitting medium in a heavy truck, bus, and so on, right? So those are typical energy transmitting medium. And finally, we have the foundation brake. Okay, the foundation brake is the one it actually does the braking action on the wheels and then decelerates the wheel. Okay, so these are the disc brakes and the drum brakes, which can be utilized to realize the friction braking action on the wheels and decelerate the wheels. Okay, so the most common realization uh, available today of this foundation brakes are the disc brake and the drum brake. Of course, there were other realizations available historically, but over time, these are the two main, what to say, realizations of the foundation brake that are available in modern automobiles. So, and interestingly, disc brakes and drum brakes present an interesting case study, in automobile history. In fact, if we look at disc brake and drum brakes, both were invented at around the same time. Okay, in the year 1942, okay, at the turn of the 20th century, people invented the disc brake and the drum brake. Okay, so but then all of us are aware that it took longer for the adoption of the disc brake than the drum brake. So the question arises why? Okay, so just let me share this interesting nugget from history, so that like we also get a perspective on this, right? So it so happens that this drum brake was invented in France, and where automotive development was very much encouraged during this time, right? So it got wider acceptance and so on. Whereas the disc brake was invented in Britain, where there were severe restrictions on automotive development at the turn of the 20th century, which may be very strange to know. But then those days, like horse-driven carriages and steam-driven locomotives, trains were dominating the transportation sector in Britain, right? So consequently, there was a strong lobby against road vehicles, automobiles, and so that that stunted the development of automobiles, right? So although today we realize that disc brakes present some very good advantages which drum brakes do not have, it really took 50 years for people to realize it because it was invented in the wrong location at the wrong time, right? On the other hand, drum brakes were invented in the correct location at the correct time. So this shows that, in addition to technical competence, we have to be in the correct place at the correct time, like doing the correct thing, right? So there is an element of chance also involved in this development. Okay, so that was an interesting bit of history in this regard. But now let's move on to technical analysis, okay, like of this brake and drum brakes. So first, let's look at drum brakes, okay, and then like we'll look at disc brakes, and then like we will look at comparison of both, right, from a performance specifications. Okay, so let me just include a simple. Oops, what happened? Sorry about that. I will just include a simple schematic of a drum brake. Okay, so that like we can figure out what happens, and then like we'll draw a free body diagram, and then like we can also look at more. Okay, so let's say we consider the schematic, right? So we consider without laws of generality that the drum is rotating counterclockwise. So we can see an element called as a brake drum, right? Which is rotating along with the wheel assembly. So these elements called as the brake shoes are fixed on a backing plate, and that is attached to the vehicle body. Okay, so they don't rotate. So there are two brake shoes, we can see them, and they are pivoted on a braking plate, backing plate. So these are pivots. Okay, and the brake shoes are attached to what is called as a backing plate, and that backing plate is fixed to the vehicle body. Okay, and we will come to the leading shoe and trailing shoe later on. But then, like, we can see that this brake shoe has what is called as a brake lining, which essentially is a friction lining of friction material, which contacts the brake drum, and then like generates the friction force or the friction torque needed to decelerate the vehicle. Okay, so we can observe that these brake shoes are pivoted about this point. Okay, these are the two pivots, and a force is applied at these two ends. Okay, so by means of, let's say, a wheel cylinder, right? So in a hydraulic brake system. So when the the braking forces, actuation forces are applied at the free ends, what's going to happen is that this brake shoe is going to rotate about this pivot, and it is going to go and contact the brake lining is going to go and contact the inner surface of the brake drum. Okay, so consequently, the brake lining is going to rub against the rotating drum, and then a friction torque is generated. Okay, so for this reason, these are what are called as internal expanding friction brakes. Okay, so internal expanding brakes. Why are they called internal expanding brakes? The reason being that, like, we can observe that the friction elements are internal to the brake drum, and then when the brake is applied, they sort of expand. That is, they go outward and then like contact the brake drum to generate the deceleration torque. Okay, so that is what happens. So we will come to this leading trailing shoe shortly. Okay, but what I have drawn here is what is called as the leading trailing shoe drum brake. Okay, so we will see what this is, right, as we do that analysis. Okay, so I hope this simple schematic is clear, right? So we are essentially having this. Of course, in today's vehicles, we have what is called as a duo servo drum brake. Okay, we will see what the duo servo drum brake is later on. But let's say first we draw the free body diagram and do the analysis of this so-called leading shoe and trailing shoe. Okay, so let's do it. So I'm once again, I'm going to do a very simple first cut analysis of this process. And we will do some lumped analysis. Okay, so let us say I draw the free body diagram of this brake shoe. Okay, what we are calling as the leading shoe. So let's just draw it properly. Please give me a second. So let's say we draw a simple schematic of this leading shoe. Okay. And this is our pivot. Okay. Let me mark all the forces that act on the shoe. So I'm going to mark some forces in dashed lines to essentially show that we are ultimately going to neglect those forces. Okay, so let's say the mass of the leading shoe is ml. So the weight of the leading shoe is ml times g. Okay, I'm sure that is clear to all of us. Now there is a actuation force acting on the leading shoe. Let's call this as F. So this is the actuation force. So how does this actuation force come about? Let us say we are driving a car and the driver presses the brake pedal, right? Through the hydraulic brake system, pressurized brake fluid comes into the wheel cylinder, right? And then like that pressure is converted to a mechanical force, which then actuates these brake shoe. Okay, so this FA is what is called as the actuation. Okay, and at the pivot there are going to be reaction forces. So let us say this is some Rx, which is the reaction force along the x-axis, and let's say some Ry, okay, which is the reaction force along the y-axis, okay, and we are going to do a lumped analysis wherein when the brake lining contacts the brake drum, there is going to be a normal load, right, which is generated along the contact area. So what we are going to do is that, like, we are going to lump all that force into a single normal load NL. Okay, that's what we are going to do. So NL indicates the normal load, normal reaction, right, on the leading shoe, okay, due to the process of braking. Please note, what is the phenomena we are considering? Let's say my vehicle is traveling, I press the brake pedal, these brake shoes are pushed against the brake drum, they are in good contact with the brake drum, and then I'm considering what is happening. So obviously there's going to be a normal load acting on the brake shoe, right? I'm drawing the free body diagram of the brake shoe. Now, when I have this normal load, there's also going to be a lumped friction force, right? Which is going to be acting. So how will this, what will be the direction of the lumped friction force? We know that the friction force is going to be perpendicular to the normal load. So let us say we consider, okay, some new brake, right? New to be the brake lining friction potential. Okay. Now the question arises. We know that this brake friction force is going to be perpendicular to the normal load. But the question is, what direction is it? Is it going to be upward or downward in this figure? So let's reason it out. So let us say I'm standing in the center of this brake shoe. Okay. So, and I'm looking at a lumped point here. Okay. When the contact is made between the brake pad and brake drum, brake shoe and the brake drum. So please note that the wheel is rotating in the counterclockwise direction. In order to develop a starting torque or a braking torque, I have to develop a clockwise torque. Okay, the friction torque will be a clockwise torque, right? Is it not? So at this point, how will I generate a clockwise torque on the brake drum? Only when the force on the brake drum is perpendicular, right? Is tangential and upward in this figure, right? Only then, if I calculate the moment about the center, I am going to generate a braking torque on the brake drum. It could be visualized in another way also. Let us say we are standing at this point, right, where I have drawn the arrow upwards, and we feel the brake shoe being pressed against the brake drum. So the brake drum is rotating counterclockwise, so I will try to move downwards, but then there is a force which is going to pull me upwards, right, to decelerate the drum. So that is why we have drawn the braking force on the drum to be upwards. Now, we can immediately see that we are drawing the free body diagram of the brake shoe. We are not drawing the free body diagram of the brake drum, right? From Newton's third law of motion, we know that there is going to be an equal and opposite reaction force. And which direction is the reaction force going to act? It's going to act downwards. Okay, so the reaction force on the brake shoe, the brake lining material, is going to be downwards. And that is the reason why we are essentially going to mark this, no, just delete this and then we will redraw this. Okay, so the reaction force, friction force on the brake shoe is going to be vertically down. Okay, for this particular shoe. I hope it is clear, like why this is the case. So let me repeat the reasoning. Without loss of generality, we have assumed the brake drum to be rotating in the counterclockwise direction. So when I am standing at a point, a lumped point of contact between the brake shoe and the brake drum, I would experience a friction force which is going to be upwards and tangential to the brake drum and brake shoe, right? At that point. So the consequent reaction force on the brake shoe will be the opposite direction, and that's going to point downwards, right? So that's why mu NL is downwards. Okay, so I hope it is clear. And in addition, we have this return spring. Okay, so we can see this return spring. Okay, so what is the function of the return spring? The return spring will ensure that the brake shoes are brought back to their original position once the brake is released. So consequently, there is going to be a reaction force or a restoring force from this return spring. Once again, I'm going to draw as a dashed arrow just to indicate that we are going to neglect the magnitude of these forces. And let me mark some what to say, geometric quantities. Let us say the distance from the pivot, okay, to the point at which the lump reaction actuation force is acting is, let's say we call it L. And let us say the distance at which the normal load is acting, let it be at a distance of P from the pivot. Okay, so this is the place, this indicates the distance at which the normal lump normal load is acting. And let us say this dimension is A, so which indicates the distance between the pivot and the point at which the lump friction force is acting. Okay, so these are some numbers, right? So which we are just marking as parameters, okay, of the drum. Okay, so I hope this construction is clear. Okay, and mu, as we just discussed, it is the friction coefficient of the brake lining. So it is the brake lining friction coefficient. Okay, so maybe what I will do is that I will use mu b so that like we are very clear about it. You know, like see, later on when we do the vehicle level analysis, we are going to use the same symbol mu to parameterize what is called as a friction coefficient of the tire road interface. So I want to avoid any potential confusion with that. Okay, so that's why we are looking at it. Okay, so we are going to consider the case where the what to say, the brake shoe has contacted the brake drum, and then the what to say, the forces are generated. Under this condition, we can see that we are going to be in a sort of like a quasi-static condition, right? So although the drum is moving, as far as the brake system, the brake shoe is concerned, it has been pressed. And although there may be some vibrations, we can neglect the acceleration due to the vibrations for this particular analysis. So we will do sort of like a quasi-static steady state analysis, right, for this particular scenario. All right. So we are going to neglect these two forces, mu Lg and F spring, and we are going to do it sort of like a quasi-static analysis, right, wherein we consider only the torques due to the various forces acting on the shoe. Okay. So balancing the torques acting on the shoe. What do we get? Okay, so let's do that. So we are going to write down the equation of motion about the pivot. So about the pivot, if you can observe, we have Fa times h to be one counterclockwise moment. Fa times h is the moment due to the actuation force. Okay. Then we have mu b times nl times a, which is the torque due to the or the moment due to the frictional force mu nl. And then we have one torque NL times B, which is the moment due to the normal load NL, okay? And we balance them, like this sum is going to be equal to 0. So please note, in general, I alpha equals tau, right? So as we know, right, the summation of the net torque acting on the system. Here we are essentially neglecting I times alpha, okay? So I alpha is taken to be almost 0. Or even if there are small vibrations, like we take I alpha to be much smaller when compared to the other quantities. Okay, so that is why we are essentially using this. That is the assumption under which we are doing this. Okay, so we are also neglecting. So we are neglecting any inertia, and then we are also neglecting spring return force. Okay,
sir,
return force. Yes, please.
sir, actuation torque, like it is, you mentioned it as L, but here you have written H, sir. FA into H.
Oh, FA into A. Okay, sorry. Okay, I just confused the terminology. Okay, sorry about. Thanks for pointing it out. So this should be what? Okay, this should have been H. Sorry, I think. Thanks for pointing it out. I just got mixed it up with wheelbase. Yeah, wheelbase was anyway capital L, but then this should have been H. Okay, thanks for pointing it out. So this distance is H. Okay, thank you. Yeah. So I hope now it's clear, right? This is FA times. Okay. So once again, FA times H is going to be. Let me write on the side so that I can explain one important concept in this regard. So FA times H is the moment due to the actuation force FA due to the actuation force FA and mu BNLA is the moment due to the friction when due to the braking force or the friction force mu and L, right? So that's the other move. Okay, so now we can observe from this particular scenario something very interesting. Okay, so in this particular brake shoe, it appears that due to the way things are set up, the torque due to friction force is in fact augmenting the torque due to actuation force. And we can also physically perceive it. So suppose, let's say we look at this brake shoe, right? The brake shoe is being rotated in this direction, okay, here. And when it is rotated, the motion of the brake drum is such that if we are standing on the brake shoe, we are going to be pulled downwards, right? Even by the rotation of the brake drum, we are going to be rotated even further in the counterclockwise direction. And the physics behind this is due to the fact that the friction force mu b times NL is generating a torque with the same sense as that of the torque due to the actuation force. Okay, so here is typically we attach a negative connotation with friction, right? But here is a scenario wherein the torque due to friction force, okay, is augmenting that due to the actuation. Okay, this phenomena is what is called as self-energization. Okay, so this phenomena is what is called as self-energization. Okay, so in fact, it's a unique jargon, like which is used in the context of drum brakes. But there are philosophical issues with this terminology because, see, as we know from first law of thermodynamics, energy cannot be created nor destroyed. It can be only converted from one form to another, and that's what is happening here also, right? So kinetic energy is being converted to thermal energy and dissipated. Okay, but then like self-energization is used in a very loose colloquial way. That is, it so turns out that this shoe is seemingly pulled further into the drum and provides more braking, right, due to this physics. Okay, so in a certain sense, it is energizing itself, right, in a very colloquial way, right? So that is how this term is used, and the brake shoe in which this phenomenon of self-energization is happening is what is called as a leading shoe. Okay, so now I hope the definition of this leading shoe is clear. Okay, so leading shoe and trailing shoe are not used in the sense of their spatial orientation. Okay, with rest in the vehicle, right? So it's just that like the way the shoes are mounted and the way the drum is rotating, whichever shoe has this phenomena where the torque due to the braking force or the friction force augments the torque due to the actuation force, leading to so-called self-energization. That shoe is what is called as a leading shoe. Okay, so just to complete this derivation, we can immediately see from the above expression that the normal load, the lumped normal load. So once again, we are doing a lumped analysis, right? Wherein we essentially are lumping all the normal loads together as one entity. Okay, so this is also, we can call it as a lump analysis. Okay, wherein we are essentially considering the distribution over an area as a single point load. Okay, so we are getting the normal load from this equation as FAH divided by B minus mu A. So we can notice that in the denominator we have B minus mu A. That's what is going to essentially improve the performance of this leading shoe, as we can see shortly. So the friction force or the braking force from the leading shoe is going to be equal to mu B times, oh sorry, this should be mu B. Okay, I use mu B. Okay, from the leading shoe should be equal to mu B times NL, where mu B is the brake lining friction coefficient. So this will be obtained as mu B FBL, sorry, not L, once again, H, okay, divided by B minus mu subscript B. Okay, so that's what will happen. And an important parameter associated with drum brakes is the so-called brake factor. Okay, the brake factor of the leading shoe. Let's denote it by BF subscript L. That's going to be sort of like output by input. See, the output from the shoe is mu NL. The input to the shoe is FA, right? Is the actuation force, right? So if we substitute the things, like, sorry, mu B and right? So once again, I think I'm just missing the subscript B. Okay, mu B and N. So this will become mu B times H divided by, oh, sorry, here also I made a mistake. This should have been FA, right? So I think, sorry, there are too many subscripts, so I'm missing some subscripts. So this is B minus mu BH divided by B minus mu BA. Okay, so that's what will be the brake factor of this leading shoe. Okay, so the brake factor is sort of like a metric that quantifies the performance of the leading shoe. And we can observe that in the denominator, we have B minus mu A, and that's going to drive up this brake factor, okay, for the leading shoe. All right. So I will leave this exercise to you. Try out a similar analysis for the so-called trailing shoe. Okay, what has been indicated in this figure, and draw the free body diagram, mark similar forces, and then like write similar equations to get an expression for the force output from the trailing shoe and the brake factor output from the trailing shoe. And we will sort of like start our next class with that discussion. And then we will figure out why we call these shoes as leading shoe and trailing shoe, respectively. Okay, so what is leading and trailing about them? That will become clear in tomorrow's class. Okay, and we will also learn why we use drum brakes and disc brakes the way we do. Okay, so once we do that analysis. Okay, so any questions on what we have done today before I close today's lecture?
So the friction force you applied mu NL, will it also have a vertical component also?
So here the way we have formulated the problem, it is NL is a lump normal force, right? So from physics, we know that the friction force is going to be perpendicular to the normal force. Okay, so that's all there is. All right. So
yeah. If you look at the surface of this brake shoe, it's a circular one, right? So the friction will be all across the surface.
Exactly. That's why I am calling this as a lumped analysis. Okay. Yeah. Okay. So I'm just taking a very simple, doing a very simple analysis to convey something. Okay. That will become clear to us in the next class. So as I told, we are not doing sort of like a distributed analysis or a very detailed analysis. I'm doing a very lumped analysis, very simplified analysis. Okay.
Okay, sir.
So obviously the accuracy of its response is going to be an issue, right? But that's okay. No, we will learn some interesting concepts from it. Okay?
Sir, will the wear will be different in the leading and the trailing shoe?
Yes, we will discuss that. Okay, so because the loads are going to be different, right? Is it not? Correct. So if you look at the loads on the leading shoe and the trailing shoe, right? The forces it experiences and the normal loads they experience will be different.
Okay.
Yeah. So we will see that the normal load on the leading shoe is greater than the normal loads and the friction forces on the trailing shoe. Okay. All right. Any other questions? Okay. So if not, let me stop recording here.